Hello friends, this is the first lecture for my channel, Introduction to the Basic Geophysical Techniques and the Study of Earth. In order, already in my introductory lecture uploaded, I have told about what the subject geophysics is actually, and how we can just study the subject by basics physics things. So myself, Dr. Devajyoti Shah, I am based geophysicist in Marine and Coastal Survey Division in GSI Visakhapatnam. So I'll be, as a physicist and geophysicist, I'll be delivering lecture both on the physics and geophysics things. So that just basic introduction that I have. Yeah. So as the field geophysics is the application of physics in geology. So the subject geology involves the studying the material that makes up the earth and the rocks and the mineral. So basically the study of it, the exposures, the outcrop, that is basically means the geology. Now, the field geophysics is the field that integrates geology, mathematics, and physics, and using the well-known physical methods like gravity, magnetic, electrical, and seismic methods. So, in order to understand how the earth works. So, literally, geophysics is nothing but the concept of physics in geology. Now, the what we actually do in geophysics, we first we have to collect the data, followed by the data processing and the interpretation, and at last in geophysics you have to correlate your geophysical data with the geology to have a to just to have a clear understanding what is your objective. The objective is at last will be with the correlation with the geology, the geophysical data. So without geophysics, geology is nothing, and without geology, geophysics is nothing. And the geophysics needs the application of all the physical methods, that's gravity, magnetic, electrical, and seismic, and that's how the total interdisciplinary subject works. So you can imagine how interesting is the subject. So while going deeper into the subject, you can gain more better knowledge on the subject. Now, this is my outline of presentation. So first I will be talking about the overview of geophysical techniques. What are the geophysical techniques and what are the properties that we are investigating with this geophysical technique? This gravity, magnetic, seismic, and heat flow. These are the four of the techniques. Now, that very basic things, that is the internal structure of the earth, that involves little more geology and little more memory wise things, but don't worry, you can easily have an understanding, and that is a very basic things of the earth. In any competitive exam you can be asked about the questions of what are the layers of the earth, uh, hmm, and now the last things is the how the techniques, that means the gravity, magnetic, seismic, that geophysical techniques helps in probing our earth, that is in the earth science, that is the geothermal gradient, and the using this property which is investigated within the earth, that is the thermal conductivity and heat flow. So you can see from these things, you can see from these methods, using the using all the things, using the property measured at the earth surface, you can measure the property investigated within the earth. So it is so much of interesting. Yes, you can gain so much of interesting things while deeper. Now, potential field method. What is means by potential field methods? Gravity and magnetics, these are the two things that fall under this category of potential field method. So in the left hand side picture, what we are showing, that is the surface of the earth, the property measure, that is the gravitational acceleration, which is always downward movement. And for magnetic things, that it depends on the direction of the magnetic field, depends on the magnetic latitude. We measure the we just employ the gravimeter that measures the gravity field of the earth, and where there is a higher density body that relates with the subsurface mass distribution. Where there is a higher density body, the gravimeter shows the higher g acceleration, and with the low density body you can have the lower g value. Same as with the higher magnetic susceptibility and redundant magnetization, we can have a this is a magnetometers, and this is a magnetic field of total magnetic field of the earth. Now magnetometer that gravimeter reveals that gravimeter is with the gravimeter we have the Earth's gravity and acceleration, and which relates to the nearby mass distribution, that is delta rho. And what is meant by potential field? Potential field means the field which changes strength and direction depending upon the position of observation. So when there is an increased source to receiver distance and source to source, there is a source of gravity field, and this distance increases, the strength of the gravity fields decreases gradually. That is 1 by r relation is there, gm by r square. So that relation, so that's why the strength decreases with this. And for magnetic field there is a 1 by r cube. So the distance, if the distance increases more, the magnetic field will be diminishes very fast compared to the gravity field. So gravity field, so depth of observation for gravity field is more compared to the magnetic field, because magnetic field diminishes very fast more than the gravity field. This is the potential field observation. Okay. And whereas gravity field relates to the nearby mass distribution, the magnetic field relates to the remnant magnetization and the susceptibility. This is the method. Next, our technique is seismic method. So, what is this? First, we will have natural source seismic method. This is the earthquake generation, and then during the earthquake the surface waves are generated, and then the ground motion that reveals the property of the material through which the earth, through which the wave encountered. So due to the natural source earthquake there is a motion, ground motion, and which revealing the property of the material. And now you can have a travel time. Travel time means source to receiver distance, that is the function of the seismic velocity of the wave, that depends on the seismic velocity of the wave. Now there is a seismic waves naturally created. When the seismic waves are naturally created, that travels as a body or surface wave. Surface wave with the surface of that, and body waves within the body. The names itself characterizes. And there's a, you can see that the seismometers are placed with for size. There is a source for refraction. There is a change in the velocity v1 and v2, so there's refraction occurs, and there is a receiver receives that, the seismometer receives that. So there is a more ground, there will be a ground movement and acceleration that I shown in the previous slide I have shown, and based on that you will be capturing that ground motion, and you can gain a clear idea of the seismic velocity of the wave. And for reflection method, the seismometers are placed same, the source, and there is this wave, the seismic wave encounters a change in the acoustic impedance, that is the change in the product of rho and v, so that the reflection occurs. So this is called the control source reflection, control source seismic wave, and whereas is the earthquake, it is called the natural source. This is this is the control source seismic waves. Next we go to the heat flow method. This is also very interesting related to the physical phenomena. Heat continuously flows outward from the hotter region to the earth's surface. As we know, there is a gradient in temperature. So due to this, the heat flow. So there is a, as we go deeper into the earth, due to the geothermal gradient, the heat flows from the outer surface to the surface of the earth. And we can measure the change in temperature from the surface downward to the drill hole. So what we do here in this inner work, a method, as I am talking about the employing some experimental things. There's a drill hole uh, is there, and there's a thermometer is placed, and we and thermometers are placed so that these temperatures, through the temperatures are measured. So by the drill hole, if we know the thermal conductivity of the rock, and the and you can use the geothermal gradient del T del Z. This is the gradient of temperature to calculate the heat flow by a formula. Q is equal to K into area of through is the heat flow A into del T by del Z. Through this formula, you can calculate the flow of heat through the surface of the earth, and these are the temperatures which are measured at the different depths in a drill hole. So now what is this application? So heat if we know the heat flow, that pinpoints a shallow intrusion or the changes in the depth to the lithosphere atmosphere transition zone, that I will describe when I'll be talking about the regions of the earth and how it is related to the heat flow. So shallow intrusion means some shallow bodies, and the change delta T, it changes where the lithosphere atmosphere region is a change in the temperature. So now in this method we are now it there now this is the slides of the internal structure of the earth. So there are three structures: onion like shells, there's a crust, mantle, and the core. Crust, it is ranging from 5 to 70 kilometer. There will be two. One is continental crust and another is oceanic crust. This is 6 is the crust. You can see that this is the outer layer. Okay, this is the outer layer is the crust, and the second is that this is the called oceanic crust. This is the average density in the continental crust is 2.7 gram per centimeter. So you can remember this is the granitic rocks and this is the basaltic rocks, oceanic crust. Now this is the portion that occupies a big region in the earth, that is called mantle, almost 84% or 82%. So the depth range is very large, 70 to 2890. There are so many, there are layers in that, but in upper layer, within the upper and lower layers, but upper layer regions extend from 210 to 270, with the lower layer ranging up to 2890. So this is the region, this is the 3 is the lower mantle, and this is 4 is the upper mantle. So this is the first crust, then lithosphere. Crust, what is lithosphere? Lithosphere is the crust and uppermost mantle. This is called lithosphere. This is the rigid sphere which is responsible for the plate tectonic movements. Okay, this is a very, so I'll be giving lectures after that. And the last layer is the core, the solid inner core and the liquid outer core. This is the two is number is, this is the outer core, this is the liquid outer core, and this is one is the innermost layer, this is the inner core, that is very solid. So based on the seismic velocities of the wave, that thing, that solid and the properties are established. Seismic velocity, because in a compact dense layer the velocity of the seismic wave increases, and in a less dense layer the velocity decreases, and there will be many phase change of the seismic wave within this region. Motion of the outer core, this liquid is responsible for the magnetic field of the earth. So as I have already talked, the crust with the uppermost mantle constitute the lithosphere, and which is floating on the asthenosphere. Asthenosphere is the very liquid portion, is a brittle ductile transition it's called, and the discontinuity between crust and mantle is called mohoroic discontinuity. It is very important things, and it is due to the change in the rock composition. So the composition through which the rocks are formed, that changes. That's why that mohoroic discontinuity appears. Okay, now now there are two things, that is continental crust and oceanic crust. I was talking about. The continental crust is the just comprises of silicate rocks, granite, sodium, aluminum. Is as you can say that it is less dense and granitic type rocks, whereas oceanic crust is more dense and basaltic rocks. That's why it subducts. Oceanic crust is just basalt, iron. It's a very heavy minerals, magnesium, silicate rocks, and both type of crust behaves as if they are floating on the mantle, because they are less dense, and mantle is more dense than the crust. Now, the very interesting thing is the oxygen is the most abundant element in the crust, so that reflects the importance of silicate materials. The uppermost mantle is called, and now you can see that one by one. This is the continental crust, this is the thick continental crust, this is the thin continental crust. Continental crust, this is the less dense, that's, and this is the more dense oceanic crust. Now the crust and the uppermost mantle is the lithosphere total, up to 150 kilometer range, and after that there is a layer called asthenosphere that goes upward due to the heat flow movement. So heat flow, that Q is equal to Kn to del T by del Z, that geothermal gradient, is related to the Earth's the motion, that is asthenosphere. Okay, and the upper mantle is called lithospheric mantle. This is called the lithospheric mantle. Below that there is an asthenosphere. So now already I have, so everything about the arts mantle told have been described. This is the upper mantle. There will be transition zone. So there is also composition of the rock changes and there will be phase change in this seismic velocity. And that is the lower mantle. This is the outer core. This is the inner core. And as I've already talked about, the below this temperature, this is very important. The rock is hot enough to flow. There will be a heat flow movement. So that region is called asthenosphere, which which is below the lithosphere. Mainly mantle is composed of ultramafic rocks called peridotite, and it is a very large arts, 82% of the arts volume, and the thickness is also very large, 2885 kilometer thick. And the crust and the core, this is the middle layer, very large middle layer already. And there is a upper mantle, already talked about. This is a lower mantle, and there is a between that there is a transitional zone. So there is a last layer, the core things. And now there are two components, that is the liquid outer core, iron, sulfur, nickel, and the solid inner core, with the outer core radius almost above 2000 kilometer. And density, you can see this you can see always the density is very high because iron, nickel, and sulfur is there, very high elements. And there is the inner core density is also very high. And the most important thing is the inner core is a solid material, and this is the outer core. This is a, you can see the convective movements in there. There is a magnetic model like geomagnetic north pole is a magnetic south pole. There's a magnetic flow lines. This is the direction of the magnetic lines of flow. Geographic south pole. This behaves like a bar magnet Earth. So during my description of magnetic field, I will elaborately discuss about this motion and how it generates the magnetic field of the Earth. That is called geomagnetic field, which is very important in perspective of the outer core movement from the fluid in flow in the outer core. So density is also very high there. Now let's talk about the benefits of the geophysical techniques in probing the earth. So up to now we have described about gravity, magnetic, seismic, and heat flow. So how gravity first, let's talk about the how the gravity method is useful in probing the earth in case of earth science. So it can be useful to map the crustal thickness. We are talking about the crustal layer, 5 to 70 kilometer thick, and already talked about that crust material is less dense than the mantle. So if we employ gravity method, that with the density change, that means delta rho, with the seeing the anomaly, we can map the crustal thickness changes from crust to mantle. And they are also consistent with the thick crust beneath the higher topography of some mountain range. The crust, because thickness and thinness varies between continental crust and oceanic crust, as the previous slides have depicted. Now from magnetic method, you know the crystalline rocks, that means igneous rocks, they are more magnetic than the sedimentary rock. So to map the igneous intrusion, we can use the magnetic observation, and it can also be used to estimate the crude depth. You know the crude depth, that below the temperature, the ferromagnetic material, if we hit the ferromagnetic material after a certain temperature, it just loses all its magnetic property and becomes a paramagnetic material. So from the geothermal gradient, we can easily see if the heat flow increases, the ferromagnetic material, the material for the responsible for the earth magnetic field, loses its magnetic property and becomes a paramagnetic material. So that cutoff depth or that depth, threshold depth, is the Curie depth. And it is very important in magnetic measurement to estimate that Curie depth, and that can be measured only with the help of magnetic observation. When so the the earth magnetic field also periodically reverses direction, and whenever a rock is formed, that magnetic field of the earth, the information is stored in the as a preserved as a magnetization in some rocks, so which will be very useful to record the geological time scale. So with the magnetic observation, this is one of the most observing phenomena that we can record the geological time with the due to the periodically reversal of magnetic field. Now, whenever there is a very high heat flow rate, that can that due to the high heat flow rate, I have already told that there is a region called shallow asthenosphere. That means 100 to 150 kilometer. So there is that is the region where when the heat flow rate is very high, and also there will be shallow magma sources, hot spot that you can also characterize as using the heat flow rate. But let me tell you one thing, gravity and magnetic fields are potential field. So the strength and the strength of the field decreases gradually as we move away from the sources. So methods sometimes these methods are weak compared to the very strong techniques like seismic reflection and refraction. So reflection method is very useful in resolving the interfaces. There are some interfaces which are defined by seismic velocity and the acoustic impedance. So these methods can be useful to map the interfaces. And whenever there is a crustal thickness change, we can use the method seismic reflection and the diffraction. And the Mohorovic discontinuity can also be identified using that. So first thing, so let me tell you one thing. This is the first thing of any geophysical measurement is the first employing the gravity and magnetic method on a large scale. So if we have any promising result, then we can move to seismic methods. So the seismic methods can give more accurate result than gravity and then the magnetic. So now you can see this is the some common geophysical books you can follow, very popular books. And thank you. uh, if you really like my lectures, please like and subscribe. More lectures I will be giving, and my next lecture will be on the application of gravity methods, the gravity field of the earth and its corresponding physical and mathematical equations, and how it can be useful in real day-to-day this application. So gravity methods and the shape of the art, which is also related with gravity things, and the most important things with the things, the how the gravity observation relate to the mass distribution after employing some correction, that means gravity data detection. So thank you.